We now return back to areas. If we're thinking about our left sum, we also talked a little bit earlier that we could make a right sum as well. What would that look like in terms of formulas though? Our standard start and end points in the x coordinates are x equals a and x equals b. Then we divide that into n rectangles or n subintervals. Then with the right hand rule, what we do is we take our first interval x0 to x1. The other ones are numbered accordingly. The last one is xn. And on the right-hand rule, what we do is we look at each interval and we go up to the graph at the right-hand endpoint. And that is simply the function value at x1. And so if we want to do a height times a width on that first interval using the right-hand endpoint as our guide, then we get f of x1. And then we have f of x2 on the next interval. And so on and so forth until the last interval, which would use the height at the last point, f of x sub n, again times delta x to get a width. So we have all these rectangles, and the sum written out long form is this, but if we want to write it using an I notation and summation notation, we just note that the first term is x sub 1, the next term has an x sub 2 in it, and so on. That's the only thing that changes term by term. So we just say, well, let's do x sub I and let I equal 1 up to n. Whether you remember the formula for this or just the concept, either one will get you to the same place. We will often write this form though, so it's important to be able to at least recognize it. As a computational example, what we're going to do is look at the left and right with 6 intervals. So whenever we put the number in here, that's our number of intervals or rectangles. And we're going to do that pictorially here, and we'll estimate some of the rectangle heights as part of that process. Our first step is to recognize the starting and end points. Okay, so there's our A and our B. We'll do this on the other side as well. What we get out of the 6 intervals is the width of each rectangle. So we're going to take our b minus a over n, so 4 minus 1 over 6, and that's going to be 1/2. And that's the width of each rectangle. This should not come as a huge shock. We're taking something that's 3 long and dividing it into 6. We're going to have 1/2 as the width of each possible rectangle. We're going to do the left-hand rule on this one. So each interval is 1/2 wide, and then on each interval we use the left-hand endpoint, go up to the graph, use that as my height, and then draw the rectangle. On this interval, we go up to the graph on the left-hand end and use that as a width. And these, once you get the pattern, pretty much draw themselves. Maybe not quite that easy, but close. There we go. And this area, which is equal to the left-hand approximation with 6 intervals, would equal height times width. So it's going to be a bunch of heights times widths. I'm going to write it out longhand first with the generic formulas. And then the last term, notice the last term that we used is 3.5. We use that height. We actually don't use the height at 4. We have one extra endpoint we don't use. In this case here, it would be x sub 5 times delta x. And then we can actually compute all of these values. We'll have heights, so a height of 1 times 1/2 plus. On the next interval, a height of 2 times 1/2 plus. Next is 3. The next one after that's pretty close to 3.5. Then 4, and then let's say 4.25. Always times the width times 1/2. And then 4.25 is 4.25. And there we are. And we should see 1, 2, 3, 4, 5, 6 elements in the sum because we have 6 rectangles in our sum. Now, of course, when we're adding this up, you can factor out the 1/2. The 1/2 is common to every term, and so we could actually write this as 1 plus 2 plus 3 plus 3.5 plus 4 plus 4.25, all times 1/2. When we do that, we get an estimate from the left-hand rule of 8.875 square units. Now we repeat exactly the same operation. It seems a little harder to draw for most people at first with the right-hand rule, just because we tend to prefer going left to right. But we imagine dividing this interval of 1 to 4 into 6 subintervals. Then on each interval we go to the right-hand side, go up to the graph, and draw a rectangle backwards with that height. On this next interval, 2 is the upper end of the interval. We go up to the graph there, and then we go to the left to complete that rectangle because that's what we're applying on this interval here between 1.5 and 2. And once you get the idea, I usually draw the heights all first and then complete the rectangles going backwards with that. And so on. And in this case, we do use the last interval, but we never use the first endpoint. So it's a bit of a change. It's a bit of an alternation from what we did on the left rule, not surprisingly, but it gives us a similar response. So here we have right of 6 is going to be equal to the height in the first rectangle. That's 2 times 1/2 plus, just going by rectangle, 3 times 1/2. And actually, we start seeing the same numbers because, wait a minute, we're using the same height as we used over here, except we're applying it to a different rectangle. The only one that actually changes is we're throwing away the left-hand endpoint, and instead on the last interval we're going to use the height on the last endpoint at the right end, and so we can actually recycle all our values here up till the end. And we have 4 times 1/2. We have the 4.25 times 1/2. That's 5 intervals there, 1, 2, 3, 4, and 5. And then on the last one, we'll use our 4.5. And when we do that, and do the calculation again, we compute a total with the halves and everything else of 10.625 square units. And notice, first of all, these numbers are closer than any other estimates we've built so far, and we can see that the area under the rectangles is much, much closer to the actual area under the curve. The error or overestimate here is just this little area on top of each rectangle, but we're avoiding some of the big swaths of area that we had when we used wider rectangles. So this idea of using narrower rectangles has a real payoff for accuracy. With that in mind, where do you think this is going to go? Well, if we use more and more rectangles, we'd get more and more accuracy. Maybe we could take a limit as the number of rectangles went to infinity or something and bring in our other calculus ideas again. We'll see that moving forward.